Hi, I'm Seth, and this is a quick introduction to sampling theory. First, I'm going to explain how we traditionally explain sampling theory, and then at the end, I'm going to kind of say, that's not really exactly how it works, and I'll give you a more complicated explanation, but let's just start with the traditional one because it's a little easier to understand. All right, so traditionally we say the population is the set of all people that we are trying to understand, such as, for example, American college students. We would like to be able to access the entire population because then our statistical models would be very trustworthy. For example, if we were curious how many hours of sleep American college students get per night on average, and we could somehow access the entire population, well, we could just ask each individual and then we could calculate the average. This would allow us to be extremely confident that we knew the average amount of sleep that American college students get, or at least that they report getting. Unfortunately, populations are usually too large for us to be able to access every single member in order to measure some characteristic. In our example, imagine trying to track down every single American college student and ask them this question. So because that's not feasible, we usually instead draw a sample. A sample is any subset of people that you draw from the population. So to explain it at the most basic level, you select some individuals out of the population, and then you measure whatever characteristics you're studying. In this case, we've drawn a sample of 4 individuals from the population. Now, a sample is kind of like a model of the population. It's like a miniature version that we can actually access. And we hope that the sample is representative of the population, meaning that its characteristics are basically the same. Because if that's the case, that means that by studying the sample, we can learn about the population. And the population is what we really care about. When we make conclusions about the population based on a sample we drew from it, or multiple samples, this is called generalizing. We take information we do have access to and we use it to make inferences about information we don't have access to. If the sample is representative of the population, then studying the sample will tell us about individuals in the population who we haven't measured. Here are a few basic definitions. A population parameter is any characteristic of the population. A sample statistic is the corresponding characteristic in a sample. So we're hoping that by calculating sample statistics, this will help us generalize to population parameters. There's also a concept called sampling variation, which simply refers to the fact that statistics we calculate are going to differ from one sample to the next because each sample is a little bit different from the others, or a lot different, maybe. A consequence of this is sampling error, which just refers to any difference between the true population characteristic, the parameter, and the sample statistic that we calculate. For example, suppose that American college students sleep 8 hours per night on average. That's our population parameter. But suppose when we draw this sample of 4 individuals, they report that they sleep 9 hours per night on average. This difference between the statistic and the parameter is sampling error. Now, there are some things we can do to help reduce sampling error. 2 of the most important things are to use random selection and to have a large sample size. If we did not randomly select the individuals in our sample, there's an increased risk that they're going to be systematically different from the population in some way. For example, if we only study certain groups of people, then we're not going to be able to generalize to all people, potentially. And that's a problem because psychologists usually want their findings to generalize to large groups of people or all people. Hopefully, it's also intuitive that as the sample size increases, as the sample size becomes closer to being the population size, the sample comes closer to being the population. The upshot is that when we calculate statistics from large random samples, they tend to be better estimates of population parameters than if we use small, non-random samples. For example, maybe in this large or random sample, we get a sample statistic of 7.8, which is closer to the true value in the population. Now, if you're happy with that, you can just close the video and be done with it. But if you want to learn a little bit more, a more advanced version of this, stick around. Okay, so the problem is everything I've just told you is not quite true, or it's a little bit too simple. I said that the population, in the traditional explanation, is all of the people of interest to you, and the sample is some subset of those people. But it's not quite right, and it can actually lead to some confusion once you start getting into more advanced analyses. Here are the more general and more correct definitions of population and sample, at least insofar as we use them in the sciences. The population is the set of all possible measurements of interest to you, and the sample is any subset of that population that you actually gather. I'm going to walk through a few examples to demonstrate how these definitions are actually more accurate. First of all, it's not true to say that the population is all of the people you're interested in, because you may not be studying people. Maybe if you're studying minerals, then the population is all the measurements of geodes that you could collect, and the sample is some subset of those. Or even if you are studying people, like in psychology, consider a scenario where you're measuring the same person repeatedly so that you can understand them as an individual better. Imagine that you measure the same person randomly throughout the day for 6 straight weeks. In this scenario, the population is the set of all measurements that you could have collected from that person over the 6-week period. And the sample is the set of measurements that you did collect during that time. So even though there's only one person being studied, the population is actually quite large. Let's do one last little thought experiment. Suppose that we somehow could access all of the people that we wanted to draw conclusions about. Even if we could measure every single person, we would still be uncertain about our statistics. For example, suppose we track down every single American college student and we ask them how many hours of sleep they get per night on average. If we track them all down again tomorrow, or the next day, or next week, they might give us slightly different answers. So even if we calculate an average based on asking every person we're interested in, we still aren't completely confident that we've got the true population parameter. Measuring every single individual would only give us a single snapshot in time. It would only be a sample of the possible measurements we could have collected from them across similar times and situations. But usually we want our conclusions to last more than 24 hours or 24 seconds. And if we want to be able to generalize beyond this single moment in time, that means our population must be all possible measurements that we could have gathered, including hypothetical ones. What all this means is that most populations are not just large, they're infinite. And that means that it's not just impractical to collect all those measurements, it's impossible. As such, we are nearly always dealing with sample data. Even if you were able to measure some characteristic of every person you wanted to draw conclusions about, you would still be wise to treat that as sample data. And that's important because we use different formulas to calculate population parameters than sample statistics. Okay, if you made it all the way to the end of the video, including going through that more advanced explanation, you should congratulate yourself because that's enough to give anyone a headache. If you have questions or comments, please shoot me an email. See you next time.